Hi, welcome to my channel on the technology space with machine learning and artificial intelligence. So the today's topic is what is a neural network. So this is the second part of a two-part series, and the link to the first part is in the description of this video. So let's dig deeper into the main slides of this presentation. We have discussed a basic component of a biological neuron and then how that will relate it to a artificial neuron. So this type of artificial neuron, at least the basic building block, can be categorized as a perceptron. So let's try to give you an overview of the perceptron or the artificial neuron, and then to study their main component and how that related to the biological neuron. In this blue box, you can see a general structure of a perceptron. As you can see, it has inputs and the main structure and then the outputs. So the main structure consists of summation, which is represented by a sigma sign. So that means adding some values, and then these added values go through a function f and then give you output a. So here I'm presenting the activation function, which is also represented by f, and we have a slight modification into this activation function. As you can see, there are two outputs coming out of this activation function, 0 and 1. 0 represent a situation where the artificial or the biological neuron is not excited itself, and then obviously 1 represent a situation when the artificial or the biological neuron get excited. And then this excitation happen in a specific threshold value, which is represented as NA in this situation. So let's move on to the next slide, where we discuss how the biological neuron is related to this perceptron. So as you can see, the inputs or the electrical sparks coming into the biological neuron go through these dendrites. So these inputs in the perceptron is represented by P1 to PR. So that means R number of dendrites in this perceptron. And then each input coming into this neuron is multiplied by a weight factor, which is represented by W value. So the W consists of W1 to WR. So that means R number of weight factors are multiplied by each one of these inputs coming into the perceptron. So then that concept can be represented in a more simplified way. So that means each input is multiplied by the respective weight factor, and then these multiplied input versus input and the weight factor is add up to get the total summation which is coming into this perceptron. And then a specific term which is called this bias also being included into the perceptron. So what bias generally does is it can adjust the inputs coming into the perceptron itself. So if you consider all the inputs, weight factors, and the bias term, it can be represented by each input multiplied by the respective weight factor. And when you add up all these components up to a R number of components, and then when you add the bias also, so the outcome would be the total summation of inputs coming into the perceptron, and then that the summation is represented by N in this perceptron itself. So you can see this, assume that cell body of an artificial biological neuron. will add up all these inputs and the bias term coming into the neuron itself. So that is what represented by the first part of this perceptron. And then the activation function. So the activation function is represented by F. So that means the summation of all the inputs multiplied by their respective weight factor plus the bias term will go through this activation function. So that means N value go through this activation functions to give you the output as A in this situation. So the output of the perceptron would be A in this slide. So when you're thinking about output of a biological neuron, there are two outputs. Either it would get excited or there will not be any output. So that situation is represented by 0 and 1. So let's try to see how we can put into a more mathematical framework of such output in this perceptron itself. So that is represented in this following equation. That means the output, the inputs coming into the activation function, this case is the N. If the N value is beyond a certain threshold value, which is NA, so then this perceptron get excited in a more biological sense. So when the inputs or the electrical sparks getting into biological neuron, if it's beyond some sort of threshold value, then the neuron itself, this biological neuron itself will get excited. So that is what represented in this mathematical formulation in these perceptron situations. Otherwise the output going to be 0. So then if I can summarize what I have said about this perceptron, that means each input coming into the neuron is multiplied by its respective weight factor, and then you add up all these components till R number of component in this perceptron, and then you also add the bias term into that. So that is the total summation of the inputs coming into this perceptron is represented by N. And then this N value go through the activation function of Fn. And then the total summation or the N value is beyond a specific threshold value, which is Na. So then the perceptron get activated and its output going to be 1. Otherwise it will not give you any output. That is represented by 0 in this situation. So I think we have now discussed more detailed version of the perceptron. So let's try to simplify this graphical representation of the perceptron itself. So for the simplification, we try to combine the summation and the activation function into a single block, as you can see in my right hand side. So that combination can be represented by graphically in this figure. And then these inputs can be distributed into a more structured way as the input layer. As you can see, inputs are distributed to a single layer with their respective weight factors. And then the combined function of the summation and the activation function is in a similar way you can represent, and the output also represented in the similar way. And then if you combine two perceptrons, it would look like what I have in the right hand side. So in this situation, we assume that both perceptrons are sharing a single input layer. But it has a 2 output, so that means there will be output layer if you're adding more than 1 neurons into this type of framework. So adding more and more neurons or the perceptrons would create these massive structures of a neural network, and that would be represented by in this figure in the right hand side. So this is a general representation of a neural network. So I think we have answered that initial question of what is a neural network. So it is more like a combination of various artificial neurons or perceptrons in a more parallel and series structure. And this basic component of this neural network would be input layer, which this is the inputs coming into the neural network itself, and then the hidden layer, which is the internal part of the neural network, and then the output layer, that is the outputs coming out of these neural networks. And when it's come to the hidden layer, this is generally preserve the most important information in the neural networks. As you know, we use data sets to train these neural networks, and then the most important information on these data sets would be preserved by these hidden layers. And then let's try to answer another important questions in these neural networks. Often people classified neural networks as a black box approach. This may not be exactly accurate in a situation, especially related to these modern neural networks. I'm referring to autoencoders, that is a part of deep learning frameworks. So in these autoencoders, often the information is preserved as vectors or matrices. So you can assume if the information being preserved in either one of these building blocks of mathematics, then we would be able to explain how the information being preserved. So that knowledge itself will make this approach may not be a black box approach, at least not anymore in this research field. So I can say the lack of understanding of how this information been preserved within these neural networks makes some people believe this is a black box approach. But I think we have some level of understanding of how this information being preserved as a vectors and matrices in these deep learning frameworks. So I would not support this black box type of a concept further into these neural networks anymore. So then the final question I'm going to answer in this presentation would be, are there many neural networks types? Yeah, there are several. At least here I am presenting some selected neural network types. I think I have discussed this single layer perceptron in the beginning. So when you combine multiple perceptrons, then you can create this multi-layer perceptron structures. Radial bias networks also, radial basis networks, RBF also another network types being utilized by the research community. And then long short-term memory, LSTMs, also another types of neural networks. And then these networks consist of feedback with unit memory units inside the hidden layer. And recurrent neural networks, another popular application, which is called RNNs, that consists of feedback units in its hidden layer. And then gated recurrent units, GRUs, also another popular neural network that consists of feedback with different memory units in its hidden layer. And then autoencoders are variational autoencoders are two of my popular neural networks. And then autoencoders, this output layer consists of match input output units. And then this variational autoencoder consists of probabilistic hidden units in its hidden layers. So these are some selected neural network types being used by the research community. So that's the end of my presentation. So hopefully you have enjoyed this presentation. So I'm planning to discuss a more detailed version of these neural networks in the sense of machine learning and artificial intelligence. So if you are still interested, please stick around. Thank you.